We have already explained what uncertainty scales are and why they are important. In this lesson, we will present the uncertainty scale developed for the critical digital model and refined within the COVER project. This scale consists of 7 levels of increasing uncertainty, plus 1 for abstention. Colors with varying shades have been assigned to the levels, ordered along the visible light spectrum, with white and black placed at the extremes of the scale. The chosen colors are easily nameable and recognizable: white, blue, cyan, green, yellow, orange, red, and black. No rigid RGB values have been assigned to the colors to ensure versatility of use. It's possible to make slight variations to the colors as long as they remain recognizable and nameable. This ensures comparability across different projects. Definitions of the various levels of the scale have been written synthetically and without overlaps to simplify its use. For a more objective analysis, uncertainty quantification is based on user-independent criteria. The first level of the scale, represented by the color white, has minimal uncertainty. Elements assigned to this level primarily derive from real-world data, for example, archaeological remains, that are reliable and reach a level of detail at least equal to that desired for the reconstruction. When real-world data is not available or does not reach the desired quality or detail, we move to the subsequent levels. The second level is represented by the color blue and has low uncertainty. Elements assigned to this level mainly come from direct or primary sources that reach at least the desired level of detail. When primary or direct sources are available but minimally damaged, inconsistent, or not sufficiently clear or detailed, we move to the subsequent levels. The third level is represented by the color cyan and has medium-low uncertainty. Elements assigned to this level are mainly reconstructed from indirect or secondary sources by the same author as the object of reconstruction, and reach at least the desired level of detail. Alternatively, they are reconstructed based on logical inferences or a selection of variants deduced from minimally incomplete or inconsistent direct sources. The fourth level is represented by the color green and has medium uncertainty. Elements assigned to this level are mainly reconstructed from indirect or secondary sources by different authors and reach at least the desired level of detail. When direct sources are not available or usable, we move to the area of the scale with a higher uncertainty. The fifth level is represented by the color yellow and has a medium-high uncertainty. Elements assigned to this level are mainly reconstructed from indirect or secondary sources by the same author. The sixth level, represented by the color orange, has high uncertainty. Elements assigned to this level are mainly reconstructed from indirect or secondary sources by different authors. When no source has been found or declared, we move to the last level of uncertainty. The seventh level, represented by the color red, has maximum uncertainty. Elements assigned to this level are exclusively reconstructed without documentary reference or based on hypothesis. Finally, the level represented by the color black is an additional level to which elements that will not be considered for calculating uncertainty can be assigned, such as terrain, elements belonging to adjacent buildings, and others. If the 7-level scale is too complex for some contexts, it can be simplified to 5 or 3 levels. These 3 versions of the scale with different granularity have been developed to propose alternative solutions in case of reduced budget, time, or complexity, while maximizing the comparability of results. In the 5-level scale, the factor of authorship is no longer considered a criterion for differentiating uncertainty. Therefore, level 3 and 4 are merged into one, as well as level 5 and 6. In the 3-level scale, on the other hand, the first 2 are merged into one, as well as levels from 3 to 6. Therefore, in this scale, the differentiation between direct and indirect sources is the only criterion for quantifying uncertainty. A flowchart has also been drawn up to help operators assigning the most suitable level of uncertainty. A numerical value from 1 to 7 and a percentage range of uncertainty have been assigned to each level. These values are useful for calculating the overall average uncertainty, for example, through the 2 formulas of average uncertainty weighted on the volume and average uncertainty weighted on the volume and relevance. The first formula is intended to be user-independent. For this reason, a weighting factor with the volume of architectural elements has been added. This mathematical expedient allows operators to obtain the same result regardless of how the model is segmented, when the same uncertainty is assigned to the part. However, this approach, albeit being objective, could bias the result in favor of the bulkiest part, but not necessarily the most important ones. Therefore, a second formula has been developed, intended as complementary to the first, which introduces the relevance factor. This factor is assigned subjectively and allows for a critical increase or decrease in the weight of the parts, considered more or less important, by multiplying them with a value bigger or smaller than 1. This result is more dependent on the operator performing the analysis, but at the same time, it could be more suitable in some cases, as architecture has a creative component, and it is not always possible to obtain appropriate results using procedures entirely independent from the scholar's critical judgment. When assigning relevance factors other than 1, it is essential to declare them in order to produce traceable and transparent results. To apply these formulas in the best way possible, it is essential to calculate accurately the volume of the different parts that makes the 3D model. Therefore, the models must be properly segmented and exclusively made of watertight solids without intersections. This may look like limitation of this method. However, architectural models that do not meet these requirements would still be limited in reuse in a scientific context. The quantification procedure using the proposed formulas can be performed manually, but due to the large amount of numerical data required to avoid errors, it is preferable to automate it. A suitable tool for this activity is Grasshopper for rhinoceros, which enables assigning specific levels of uncertainty to groups of objects, allows reading the volumes of the various parts automatically, and uses this data as input for the formula. Furthermore, in the future, repositories of 3D reconstructive models could implement a similar system to automatically return these values when uploading the model and its uncertainty analysis.